Welcome to a quick video on dilution. In the previous video, I talked about strong versus weak, and those terms, strong and weak, have absolutely nothing to do with dilution. Remember, something that is defined as strong means it dissolves, nearly dissolves. Okay, let's see if I can spell today. Dissolves nearly 100%. And weak, it does not. These terms are not, dilution and strong, are not the same. They mean totally different things. Dilution describes the amount of water. So for instance, if you take a look at this picture, we have something very diluted and something very concentrated. Is it possible to have something concentrated and be defined as weak? Absolutely, because weak is a chemistry term that describes what the ions do in the water. Could you have something diluted and strong? Absolutely, you could. A strong acid dissolves nearly 100%, but if you put it with a ton of water, it is a diluted strong acid. We use molarity, the big M, to represent strong and dilute. And the bigger this number is, the more concentrated something is. And I think I just said strong or dilute, didn't I? Well, forget everything. If something has a large number, it means it is concentrated. I'm going to erase all the ink on this slide, just not to confuse myself. All right, here we go. So if something has a large number, we say it's concentrated. And if something has a low number, it is more dilute. Because we measure molarity in terms of moles per liter. The smaller this number is, the smaller that number is. About dilution is that take a close look at these pictures and then I'll tell you the cool thing. For instance, I have 12 molar hydrochloric acid, very concentrated stock solution. Well, we don't use that in labs, so I need to add water. Say I'm adding water to make a 4 molar hydrochloric acid solution. What in here does not change? Well, if you said the number of moles, you're absolutely correct. The number of moles will not change when you dilute something, just the amount of water. So we can use a dilution formula, where M1 is your initial molarity, M2 is your initial volume, to your final molarity and final volume. I'll do more of these in class, but this is an example of what we might be doing. We have a 16 molar sulfuric acid solution that we need to dilute so that in the lab we can have this molarity, and I need this much of it to run the lab. So I like to get rid of all that word stuff and write down what I have. And if you recall, the formula is M1V1 equals M2V2. And I'm not even going to write units. I'm just going to plug it in. All right, we have a 16 molar solution, and I don't know the volume that I need of that. But I do know that I need this molarity of a solution, and I need 1.5 liters. So now I simply solve for X. That means I need to measure out 0.0094 liters of the 16 molar solution. Well, actually, I'm going to change that to make my life a little more easy and say 9.4 milliliters of sulfuric acid. So I'm going to take 9.4 milliliters of the 16 molar sulfuric acid. Now, to let you know how you should do this is if I need to make 1.5 liters of this solution, ideally, I would have a volumetric flask. that measures 1.5 liters, but we'll pretend that we do. So I'll take a volumetric flask, which I cannot draw, so just bear with me. Okay, now these have these fine little lines over them. You always add acid to water, so I'm going to put the water in. It's a very exothermic reaction, so you want to make sure that you have water. And we're going to assume that this is a 1.5 liter volumetric flask. Then I would add the 9.4 milliliters of water into the flask. Then I would fill the remainder with water. In the absence of a good flask, and if units, sig figs are not a big deal, you need, an approximate 0.1 molarity solution, it doesn't matter. Another way you could do it is you could use a graduated cylinder, and I would measure out, hold on, I'm doing math on a calculator. Let's see, 1490.6 milliliters of water. Oh yeah, somebody should have yelled at me for that one. H2SO4. And then I would add the acid to it to give me a final volume of 1.5 liters. Up next, precipitation reactions.